All right, let's talk about compilers. That kind of magical black box that takes the code we write and somehow turns it into something a computer can actually understand and run. We're going to peek inside that box.
I mean, think about it. We're writing in these really expressive languages like Python or C++, but our computers, they're simple. They only get the raw stuff, ones and zeros. So how does that translation actually happen? How do we get from our thoughts to their language?
Well, at its very core, a compiler is just a translator. It's the critical bridge between the abstract code that we as humans can read and write and the concrete, simple instructions a processor needs to do its job.
But the compiler is really just one piece of a much bigger puzzle. You've got preprocessors, assemblers, linkers, a whole system working together. But for today, we're going to zoom way in and spend all our time right inside that compiler box. So to make this real, let's pick a hero for our story, and it's going to be this simple line of code. We're going to follow it every step of the way as it gets pulled apart, understood, and totally rebuilt into something completely new. Think of the compiler's whole process like a two-act play. The first act, the front end, is all about understanding the story of our code. What does it mean? And the second act, the back end, that's all about performing that story for a very specific audience, the computer it's going to run on. So, the front end's entire job, its only job, is to analyze the code and figure out its meaning. And what's key here is that it's totally focused on the rules of the programming language itself. It doesn't care one bit what kind of machine this will end up on. Okay, first up, the lexical analyzer comes in and acts like a scanner. It reads our line of code, but it doesn't see a string of letters. No, it sees a sequence of meaningful words, or what we call tokens. So position becomes an identifier, equals is an assignment operator, 60 is a number. Suddenly, our code isn't just text anymore, it's a structured sequence of concepts. This next part is kind of like having an English teacher for your code. The syntax analyzer checks the grammar. Do these tokens, in this order, actually follow the rules of the language? It builds this tree structure to represent the grammar, making sure every piece is exacted where it's supposed to be. But here's the thing. Just being grammatically correct isn't enough, right? The code also has to make sense, and that is the job of the semantic analyzer. It's smart. It sees that rate and initial are decimal numbers, and it knows you can't really multiply them by a plain old whole number like 60. So, to make sure the meaning is correct, it converts 60 into a compatible type, 60.0. Now the compiler truly understands the intent of our code. So after the front end has a complete picture, it gets the words, the grammar, the meaning, it needs to hand off that understanding to the next stage. And to do that, it creates this universal, language-agnostic blueprint. And this, right here, this is the great divide in a compiler. This blueprint is called intermediate representation, or IR. Look at how our simple line of code has been broken down into these generic, simpler instructions. This IR is the only thing the backend is ever going to see. It has absolutely no idea what the original code looked like. It only knows this universal format. This fundamental split is really the key to all of modern compiler design. You have analysis, that's understanding the code, and you have synthesis, that's building the final program. One half understands, the other half builds. Simple as that. Okay, let's head over to the back end and see how it builds the final program. Its whole job is to take that generic blueprint, the IR, and make it super specific and efficient for whatever computer we're targeting. Now, this step is technically optional, but wow, is it powerful. The optimizer looks at the IR and thinks, how can I make this better? It might notice that we're multiplying by a constant number and decide to do that math right away to save time later. This is the part that can make your program so much faster without you ever changing a single line of your original code. And here we are, the end of the line for our hero. The journey's complete. Those generic IR instructions are finally translated into the specific language of the target CPU. Commands like LDF for loading a number or multf for multiplying. The code is now in a form the computer can actually execute, for real. So, why go through all of this trouble of splitting the compiler into these two distinct halves, a front end and a back end? Well, the answer is flexibility. Incredible flexibility. This design solves a huge, huge problem. Just picture this. You've got, say, 5 programming languages, and you want them to run on 10 different kinds of computers.
Without this split, you'd have to write 50 separate compilers. It'd be a total nightmare. But with this design, you just build 5 front ends, one for each language, and 10 back ends, one for each computer. You just turned a 50-unit problem into a 15-unit solution. And that is the elegant secret sauce that lets one single language run on everything from your phone to your laptop to a giant supercomputer. So, if you want to boil it all down, it's this. The front end is the language expert. It knows everything about C++ or Python or whatever. The back end, that's the hardware expert. It knows all about Intel chips or the ARM processor in your phone, and they meet right in the middle at that universal IR. So, here's a quick look back at that whole journey. You can see the front end's 3 phases up top are all about analysis, just breaking the code down and figuring it out. And the back end's phases below, they're all about synthesis, optimizing and building the final product for a very specific machine.
So I guess the big takeaway is that this elegant front-end/back-end design doesn't just make our code work. It's really what makes the entire world of software possible at the scale we see today. It's what gives us portability, efficiency, and the power to create new languages and target new devices without having to start from scratch every single time.